Hello student, welcome to the wave optics course. Today we have lecture number 23 where we continue the concept of Newton's ring, the formation of Newton's rings and few more aspects of this topic. So let me write. Today we have lecture number 23. So we already introduced how Newton rings are formed and how from that spectra, I mean whatever the fringe pattern we have, from that fringe pattern how one can figure out the wavelength of the unknown light. So today we are going to study few more aspects of Newton's ring. So first let me draw once again the basic structure of the Newton's ring, where we have this kind of a glass plate over which this is the contact point of the glass, and then this a plano-convex surface, and then this is O is the center of the curvature that it has, and the light falls here and then reflected back from this surface, and another light falls here and reflected back from this surface, and these two lights are essentially interfering with themselves to form a pattern. And in order to form a pattern, they should maintain a phase relationship among them. So suppose this separation from here to this is say T of m. So that is the path difference from which we can calculate the path difference, and we calculated that for maxima, we have the condition 2n Tn 2n Tm, where n is the refractive index of this region. Normally it is air and it is 1, but let us put, for the generality, let us put this value as n. Then that value is 2m minus 1 lambda by 2. This is for maxima. Similarly for minima, one can find out that this path difference should be simply 2m of lambda by 2. So the first case, it is an odd multiple of lambda by 2 for maxima, and for minima we have the even multiple of lambda by 2. So here the m value can goes from 1, 2, 3, etc., and here the m value takes 0, 1, 2. So at this point you may note that at the contact point, the value of Tm is 0. exactly at the contact point the value of Tm is 0. So, from these two equations one can easily figure out that this condition can happen for minima. So, that means at contact point, since Tm equal to 0, one can get a dark spot, at center. So at this, so if I draw a structure, neutron string structure, which are concentric circles, this is the fringe pattern that one can see in this experiment, but the central spot will always be dark in this setup because of this condition. So, after having this condition of maxima minima, we can play with this and try to find out few more interesting aspects. So, and also one important thing we calculated, and that was the so let me draw it here only. So, the fringe are formed based on the structure, and suppose some maxima is here at the point Rm. R is measured from this. Then we calculated that Rm for maxima Rm was root over of 2 of R T of m. That we figure out also in the last class. That means, if we know the path difference, if we know the thickness and if we know the R, then we can calculate the value of Rn, or in other way, if I calculate Rn and R is known, then you can calculate Tm. So, that is the formula for Rm. Now, utilizing this formula, we can figure out few more things, more interesting things. So, let us do that. So, for already we find that for maxima, one can have, so what we get here is 2 NTM 2m minus 1 lambda by 2. So, that I should write here. So, for maxima we get 2n Tm, that is equal to 2m minus 1 lambda by 2. Here m goes to 1, 2, 3, etc. In few cases it is also written 2m plus 1 lambda by 2, but these are same. In that case, m can also take the value 0. Well, from here we can find out that Tm for maxima should be 2m minus 1 lambda by 4n. So, that is the value of Tm. So, if I incorporate also, we had for bright fringe, Rm is equal to it is root over of T root over of 2 of R of Tm. Now Tm is this quantity. So for bright fringe, the radius is this. That is the value, or this value. I can simplify that R 2m minus 1, and then it is lambda divided by 2n, where m is integer, takes the value 1, 2, etc. So that means if suppose we have a bright fringe here, a neutron string, so I am calculating the value of Rm of that bright fringe. So if I now calculate what is the diameter of this bright ring, so diameter of the bright ring, diameter of the bright ring is simply dm is equal to 2 of Rm, 2 multiplied by the radius, that is the diameter of the bright ring. So then we can write that dm square is simply equal to 2m minus 1 into R lambda whole divided by 2n into 4, or diameter should be 2 into 2m minus 1 lambda R by n. That is the diameter of the bright ring. So what we are doing here, try to do to find out what should be the difference of the mth and say m minus 1th order dark ring, because if I manage to get that value, then we can find out that how the diameter of the ring throughout the length is varying, and we will see that this value is a function of m. So that means over the distance, the diameter of the ring, the width of the diameter of the ring will going to be affected by this. So it is not same for all the rings. So if I calculate this for a bright ring, then for a dark ring, we can simply have dm is equal to just putting 2m minus 1 instead of putting 2m minus 1 multiplied by lambda by 2, we should put 2m multiplied by lambda by 2, and if I do, we will go to get a term like 4m lambda then r divided by n. That should be the value of the diameter for a dark ring, mth order dark ring. Now mth order dark ring, so suppose this is a dark ring, . is a central ring, and this is a dark ring. Another dark ring can also be possible here. So, this dark ring is say mth or m plus 1th dark ring. And this is say mth dark ring. So, m plus 1th dark ring and mth dark ring, I know the general formula of the diameter of mth dark ring. So, I can write that dm square is equal to 4 of m of lambda r divided by n. So, the difference of the mth and m plus 1th order dark ring in the diameter can be calculated simply by just putting m to m plus 1. So, what I am trying to do is difference in the diameter diameters of m plus 1th and mth dark ring. You can do that for bright ring also. Mth dark ring is, so that difference, if I write delta dm, that should be dm plus 1 minus dm. Now, from here we can write dm plus 1 square is equal to 4 lambda r divided by n into m plus 1. So, if I simply put this result here, then it should be 2 root over of lambda r by n and then root over of m plus 1 minus root over of n. Now, this value is independent of m. So, that means if I increase the value of m, then the separation will going to be smaller and smaller. So, one should note that for a large m, the value of delta m is small. That means the rings gradually become narrower as their radii increases. Radial increase. So that means if I look a Newton's ring, we can see that the separation between these two rings, consecutive dark rings, will gradually reduce. That means over a large distance, what happened, that the rings are gradually become narrower, and that is a feature, that is interesting feature of Newton's ring. So if I see the ring, then there are many ring structure available in this superposition of two light indifferent system. You can also see there is a Michelson interference problem, where also we have a circular fringe kind of pattern. Here also we find a circular fringe, but the identity of this kind of fringes is this quality, that if delta m is small, then the rings are gradually become narrower. So that is one aspect I wanted to discuss, and then next, that is important, that how somebody can measure after that, how somebody can measure the fringe, the width of these rings, because these rings are not like this line, it should have some width. If I draw one ring very close, my drawing is not perfect, but try to draw. So this is one ring. So now this is one like a fringe. So I want to find out what is the fringe width of this system, and that one can also figure out exactly the way we figure out for the case, that how the width will going to, how the separation between these two fringes are changing. So here we are determining fringe width. So it is simply fringe width calculation. So we already have for bright ring. So let us start with the bright ring in this case. So for bright ring, we have dm square is equal to 2 into 2m minus 1 lambda r divided by n. What happened for the next ring? M should be replaced by m plus 1, that's all. So we should write at 2 lambda r divided by n, and then 2 m plus 1 minus 1. So once we know d this is square, dm, the value of dm and dm plus 1, square of that, then we can calculate this. So their difference. So dm plus 1 square minus dm square is simply this minus this, and it is easy to just check. It is 2 lambda r divided by n. If I take this term common, then rest of the term is simply 2m plus 1, 2m minus 1, 2m plus 1 minus 2m minus 1. So we should have simply a 2 term here, and that leads to 4 of lambda of r divided by n. Now, these I write as dm plus 1 square minus, not square, dm plus 1 minus dm and dm plus 1 plus dm. That will be equal to 4 of lambda r whole divided by n. Now, we checked in the previous calculation that when m is large, then the separation between m plus 1 and m minus 1 is reduced. So, this value I can write as this is equivalent to 2 of d of m. If that is the case, then we simply have dm plus 1 minus dm, that value is equal to 4 of lambda r divided by 4 of lambda r divided by 2 of dm, which is equal to 2 of lambda r divided by dm. Straightforward calculation I am doing. I am showing that how utilizing the expressions I can find out many aspects or different results related to the structure of the pattern, the fringe pattern. So, the fringe width, interesting quantity, fringe width beta, which one can define as dm plus 1 minus dm divided by 2, because we are dealing with diameter, that is why I need to put it divided by 2, is simply lambda r whole divided by n dm. Again, you can see that beta is inversely proportional to the value of dm. That means, if I go to the higher order fringe, then the beta value will reduce compared to the lower value of radius. Finally, I like to show another thing, that how one can determine. Last day we discussed this briefly, that utilizing this Newton's ring structure, one can also determine the refractive index of a liquid. So, this is determination of the refractive index of a liquid. So, the structure is simple. In one case we have the conventional setup, where this planar convex lens is placed on a glass block, and this is here, this quantity is air having refractive index Na. In other case, what happened, that I have this structure, this planar convex lens is here, but instead of air we have some liquid placed here. I am setting this region to, so this is now liquid with some refractive index, say NL. Now this is case 1 and this is case 2. So for air, we can calculate this quantity that we already calculated actually. So I am not going to go in detail, that dm plus p minus dm square, this is for air that we calculate, and this value is 4p, where p is the order, lambda r divided by Na. Exactly the similar thing we can do for the liquid, where we can calculate this quantity, that dm plus p square minus dm square. For liquid, under the placement of the liquid, I calculate this experimentally. Now the left hand side I can calculate experimentally. So if I now divide these two equations, we simply have dm plus p square minus dm square, which we calculate experimentally, divided by dm plus p square minus dm square. This is liquid. Also this can be calculated experimentally. Both the thing we calculate experimentally, which simply comes out NL divided by Na. For the air, normally Na is very close to 1, then utilizing this expression, one can simply find out what is the value of the refractive index of the liquid by just calculating the left hand side using the experiment setup. So with that note, I like to conclude here. I don't have much time to discuss more about this, but roughly we cover the Newton's ring problem. This is extensive problem. In many cases it is used in I believe the students who are taking this course, in their lab also they may have these experiments. That's why I wanted to go through these things in a detail, and I show all the aspects of the formation of the Newton's ring and the related calculation. In the next class, what I'll do is I'll going to calculate that what happened when we use some sort of interferometer, optical interferometer. And what is optical interferometer? It is a system. That system is such that changing the cavity, that means changing the length of two mirror or two plate, I change the part difference. Essentially I am changing the part difference, and by changing the part difference, what we can do, we find the change of the the pattern, the interference pattern that is produced, and from that also we can calculate few things like wavelengths, etc. So that we are going to cover in the next class. So with that note, I would like to conclude here. Thank you very much for your attention, and see you in the next class.